So now in this part of the lecture series, we shall learn about the cable analysis. So cables are itself a very unique structures, and we have studied much about the cables design or cable analysis in our graduation. But how we can model and analyze them in real with the help of STAAD.Pro software. So, but before starting all the cable analysis in the STAAD, I just want to give you a brief review, or brief introduction of what exactly are the cable and what exactly do you mean by cable analysis, and what are the theoretical basis of them. So for that, I have opened this page from the robot structure analysis. So this is also very good software for designing, but I'm just explaining you about this cable structures. So cable structures are structures with cables as the main load carrying elements. So this is the number one approach. So if one of the main dimension of an element is bigger than the two remaining ones, and section rigidity with respect to the bending and torsion is small in comparison to the tension rigidity, such an element is regarded to be a cable. So this is the criteria for deciding whether the structure is a cable structure or not. After that, the basic conclusion drawn from the previous definition is that only tensile force can be applied to the cables. So this line is nothing but the common sense, because when we are talking about the cables, we are talking about either 40 mm, 50 mm or 60 mm steel wires. So you cannot apply compression on these cables. You can only apply tension on them. So this is the number one point that you should keep in your mind, that never apply compression load to the cables. And however, in some cases, small bending or torsional moments and shearing force can be applied to cables, but I want you to focus on the word small only. So that is not much significance, but the only significant force that cables are capable to carry is the tensile force itself. And the most significant advantage of using cable structure is the fact that cables have great admissible tensile stresses. So as the basics of the RCC structures, we know that concrete carries compression and steel carries tensions. Same is the case with the cable structures. So that is why they are made of steel, because steel have very high tensile strength. So therefore you can design a cable, or you can use a cable section in such a way that you can design light, economical and aesthetic structures. So the prime example of cable structures is the cable suspension bridges. So there are two advantages of using cable elements in design structures. Number one is that entering the initial cable tension regulates the internal force and makes the result much more effective. And second is the simple assembly, such as the suspension and assemblage of an entire structure because of its lighter weight. Now the theory part. So theory of cable structure is based on the following assumptions. Loads and other external effects are of quasi-static type and constant in time. They are not dynamic. For cables, no bending moments and shearing forces are considered. So that is also another theoretical concept. Cable elements work in the elastic range only. After that, any loads can be applied except for the moment loads. That again is what we have discussed in the upper section also, that cables can only carry tension forces only. Large displacement du but small gradients du by dx are allowed, and cable section area of F is constant, and unload cable length is equal to L. Now, what are the equations that governs this problem? So for that, they have given this two figures, figure 1a and figure 1b. So here basically it is saying that let us consider a small sag cable. That is a cable for which the angle between the tangent in any cable point and a straight line joining its end is small, loaded with an arbitrary load in its plane. So let us consider an infinite cell element in this cable, which is described in the initial stage as by the load Q0, temperature T0 and tension H0. So these are the basically the infinitesimal element which is carrying all these forces here. And after that, when the load is applied to the cable, the length of elementary section is equal to ds, that is this part here. And they are basically, this is before applying force and this is after applying force diagram. So now, assuming a small cable sag value and taking into account the total cable force must be tangent to the cable, you can assign the appropriate cable elongation as a function of only static values. So here we can see that basically this is the first stage initial, and this is the second stage, that is final. So this is H naught plus R naught B, and this is H plus RB, Q naught X and QX, and H naught R naught A and H R A. So this is the difference between the initial and as well as the final. So why we are talking about this initial stage and final stage? Because we want to come to this particular equation here, that is L2 minus L1. The difference between the after application of force and before application force is nothing but delta. That is nothing but HL divided by EA minus H naught L divided by EA plus alpha delta T plus delta minus half of this particular very large integration equation here. So this is the equation which is used in almost all the softwares. It is used in robot also, and it is used in STAAD also. So after that we can also study another all the other parameters also. So we can also open some other related information here. So this is just an information of how we can like what basically is the cable definition, and if we want to see the remarks also. So the definition of initial tension force in cable should be well thought out. So value of tensile forces or stresses specified in cable definition are the exact values required by the algorithm in the assembly load case with the appropriate cable measured along its chord. So this is also another practical example. So this is the example that we shall do in this particular lecture here. So this is nothing but we can assume it as a mast tower, or like as these can be considered as cable elements, which are in real called as guy wires. So that I shall explain you in the next few minutes, but I like want you to go to this website here and open this page and read it properly. But now coming to the concept that what exactly is this is just a theoretical image here. What is the practical image for this? So we can open this Wikipedia page here, or we can see this example here. So here in this example we can see that basically this is the mast tower or a radio tower that is suspended by these cables here. So you must have seen them in the real life also. If you are a site engineer, you must have seen a lot of these structures in real life. So basically the structure is like supported with the help of cables itself. So there are many other practical structures also. So this type of like guy wire is supported from the ground like this. So this is a dead man anchor here. So this particular concrete block is called dead man anchor, and this is called a guy wire. And here you can see some like turnbuckles here. These are also called turnbuckles in the site language. So when we like rotate this turnbuckles here, we can apply much more tension in these cables here. So to study this, we can go to the Wikipedia page also of this guy wire here. So there also like theoretical consideration when we see this type of yachts. So that you must have seen in various movies also. So this is nothing but a guy wire supported mast or mast tower. So these are called antenna mast guy wires. So this is the cylindrical strain insulator of type used in unipole and antenna mast guys. So this I had already taught you that this is called a dead man anchor here for like suspending the guy wires. So if you want to like go much more deeper into this, you can like Google this guy wire and Google the guide structures. So coming back to our like STAAD software, in this lecture we shall try to like model a simple tower or a hollow pipe tower with the cables. So this is also another funny problem that most of the 99.9% people can solve here, that this is 50 feet and this is 70 feet. What exactly is the length of this wire? This is nothing but Pythagoras theorem. So under root of 70 square plus 50 square shall solve this problem. So coming back to our lecture here, now we like need to model a simple tower with some guy wires. So So in the next lecture, first of all, we shall model this type of arrangement. So in this lecture, we shall learn how we can model and analyze a mass tower with guy wires. So basically we can check what exactly shall be the tensile forces in the cable, and then accordingly we can check them. So first of all, to start this lecture, first of all we shall prepare a basic model. So to prepare a basic model, what we can do is that we can go to the editor file and then enter units as meter kilonewton and joint coordinates on the origin itself. So this is basically the node that we have modeled at the origin point. After that we can enter y as 12 meters here. So basically this shall be the point on which I want to support all the wires here, and then we can select again, copy this element at y equal to 4 here. After that I want to so basically this is the mass tower that we are talking about. We in this example, to consider the things as simply, also to make this lecture simple, I am just assuming it to be a simple cylindrical pipe here, like a pole tower. So after that I want to support this 16 meter height pole tower with the help of the guy wires. So what we can do is that we can just copy this joint here, and then we can press enter or enter X as 9 meters. So selecting X equal to 9 here, we can model a cable here. After that again we can copy paste this particular joint as X equal to -9, and then we can again model the wire here, and then after that we can go to this element as Z. So again we can select this Z as 9. So we can model the third cable here, and if we want to see the side elevation, the side view shall be like this. So now this is just a Pythagoras theorem that we are talking about, that this is 12 meter and this is 9 meter, this should be 15 meters. So it is nothing but 81 plus 144, but it's 225, and 225 is the square of 15. So coming back to our point here, so this is the simple mass tower and these are the simple guy wires. So now basically the basic modeling is now done. After that we need to enter the properties here. So we can enter the simple hollow pipes also. So to enter the hollow pipes, we need to go to the section database. We can go to the Indian and we can select the pipe section here, and we can define the outside diameter as 0.2 and inside diameter as 0.194. that is the 200 mm and 3 mm thickness. So left click on add here. After that we can go to define and circle and select the diameter of the wire as let us suppose 30 mm. So we shall enter y as 0.03 here, and then we can select all these wires here. So now all the properties have been assigned. After that in the support page we need to create a fixed joint below this, and we can create pinned joint below these wires here. So now the supports are also done. After that we need to assign the most important part, that is specification. So under the beam section you will see there is a section called cable. So we can either assign initial tension or either we can assign unstressed length. So unstressed length we can assign it to be 14.97, supposing the 0.03 meter as the difference between, that is delta. So we can left click on add here, and we can assign this particular length to all these members here. And after that, now the specifications are done. After that we need to go to the loads, and the loads we can enter the dead load itself, And in the dead load, first of all, we always need to enter the self weight, which we can enter it as -1. And after that, if we want to check the like behavior, or to make the thing simple, I'm just adding in another point load at the top. So we can go to the nodal load and select fxs 5 kilonewton, and we can select this particular joint here. So now basically we shall check that when this type of arrangement is facing a force of 5 kilonewton or 500 kg on the top of this tower, what basically shall be the like forces in all these members here. So now the material is also assigned. Material should be steel for the whole structure here. After that, specifications are also assigned, supporting conditions are also assigned, loading basic is also assigned. Then we need to go to the analysis. So in analysis, there is an option called perform cable analysis. So in this lecture, we shall do only the simple cable analysis. So we shall left click on add here. And after that, we can go to the post print command, and we can go to define command. Here we can like select the cable sack command also. So now the cables can be selected to check the cable sag cable sag values, and after that we can just analyze the structure. So when we go to the output file here you can see that it is showing us the warning that equilibrium iteration limit has reached and cable analysis for this case has stopped. So basically the problem is that we are doing the basic cable analysis. So to avoid that, what we can do is that we can go to the analysis and perform cable analysis, and then left click on advanced cable analysis, and then left click on add here, and then just delete this option here. And we need to define this command again, that is cable sag command. We need to go to post print cable sag, and then left click on add here. So again we need to analyze this structure. So here we can see that now the analysis has been done. Here it is not showing that there is some problem in the analysis, except for the instability warnings, and these are the cable sag values that the software has calculated. So now the thing is, that if we want to see the tensile forces in the cables here, so that was the basic purpose of doing this whole exercise here. So we need to go to the post processing, and here we need to go to the beam, and then we can check the graphs here. So here we can see that in this particular cable there is this tensile force of 3.48, and this basically 203, and in this basically 215. So basically the problem is that this cable is out of line of this force here. So that is why the like both of these cables are in the tensile mode, but in this cable only the some like minimum forces are coming in this particular cable here. So what we can do to activate this cable is that we can add in another loading along this particular direction here. So we can go to dead load, nodal load, and then we can enter FZS, let us suppose 5 kN again. So we can select this particular joint again here. I want to apply force along this direction. So when we go to the post processing mode again, and then if we check the beam and graphs again, so here we can see that now the force value has increased. And there's this one more thing that I want to make it clear, that this is a very important parameter here. So instead of, let us suppose 14.97, if we enter 14.7 here. So if we change this command here, and then again we analyze this structure here. So when we go to the post processing and check the graphs here, so here we can see that how much force has increased. It is increased by almost 10 times here. So initially we were getting 203 kN. Now this force has increased to 2125 kN. So that was basically the delta L that I was explaining you when I had opened the robot analysis page. So that unstretched length is the most important parameter when we are doing the cable analysis. And obviously both of these graphs shall be empty, because there shall be no bending moment and there shall be no shear force in the cables. So this was just an exercise here that you should see, and we can go to the labels, scales, apply immediately, and so here we can see that basically the blue is the tension, and brown is the compression. So basically this member is getting compressive force here, and these members are getting the maximum tensile forces here. So we can also go to results, view value, beam results, and axial ends, and annotate. So here we can see that this is basically 2110, and this is nothing but 2120 kilonewton. So I hope the things are now clear at the end of this lecture, that basically how we can do the cable analysis, and what exactly are the specifications required for the cable analysis.